So now our goal is to come up with an equation for the parabola. In order to do that, I need to put some coordinates on the points that I have up here. And I can't do coordinates without x and y axes. And so I'm going to assume for a moment that the axis of symmetry is the y-axis. Okay? And I'm also going to assume that the x-axis runs through the vertex, so that the vertex is actually positioned at the origin. Now, I could really put the vertex anywhere, and I could orient this thing anywhere. This gives us just a nice situation where where everything plays out nicely, and the arithmetic goes well. I've got some, coordinates that'll be 0, things like that. But really, we could do something similar for any orientation of this parabola or position of the parabola, and I'll show you in a few minutes how the equations will be altered a little bit. Okay, so let's for a moment assume this. So I'm going to write my assumptions in here. Actually, I'm going to put it right here. So my assumptions are that the axis of symmetry is the y-axis. I'm going to assume that the vertex is at 0, 0, so it's at the origin. I'm also going to assume that this parabola opens up for the purposes of this example. And I'll explain in a few minutes how this will be altered if we move that, rotate it, or shift it around. Okay. So with these assumptions, and there's one more assumption I should make, and that is that the distance between the vertex and the directrix, I'm going to give a name, I'm going to call it A, the distance A, and the distance from the vertex to the focus must be the same. I'm going to call that also A, all right? Because we said the vertex is halfway in between, which must be true because its distance, because it's on the parabola, its distance to each of those, the focus and the directrix has to be the same by definition, okay? So now, each of those features of the graph have a coordinate. The focus, the vertex, we already have the vertex's coordinates. The focus now, F, is going to be at the point 0, A, right? 0 in the x direction, A in the y direction. And the point P is just going to be any arbitrary point. We'll call it xy because we want variables to represent arbitrary points on the parabola. Okay, so that gives us 3 points now. I also know that the directrix has an equation. Equations of horizontal lines are always y equals a number, and the number is the number of that y-intercept, which, because it's a units below the x-axis, will be at negative a. So the directrix is the equation y equals negative a, right? Now that tells me that the intersection, or I'm sorry, the distance from P to D, from the point to the directrix, is equivalent to the distance from the point P to the point that is directly beneath or perpendicular to the directrix, or on the directrix but perpendicular to P, right, on a perpendicular direction here. And so this point also has coordinates. It corresponds to the same x coordinate as P, but now has the y coordinate of the directrix, which is negative a, right? And so I can find these two distances, or at least algebraic representations for those distances, using the distance formula and the corresponding ordered pairs for the points that I have up here. So let's go ahead and try that. Let's look at the distance between P and F. Now the coordinates of point P are xy. The coordinates of point F are 0a. And so if I want the distance between them, I use the distance formula, which, if you recall, is a derivative of the Pythagorean theorem. Comes from the Pythagorean theorem. It's the square root of the horizontal change plus squared plus the vertical change squared. Okay, so a squared plus b squared equals c squared. And so from P to F, I want the horizontal distance, which is just the difference in the x values. So we'll go x minus 0 squared plus the vertical distance, which would be y minus a squared. Okay, so that should give me the distance between P and F. And so this is an algebraic representation of that distance. All right, so now if I go through and maybe simplify this for just a moment, I would have, let's see, the square root of, this is x squared. And of course, I could expand this out. Y minus a quantity squared is really y squared minus 2ay plus a squared. However, that's really not useful. Oh, yes, it is. Yep, that is useful. We'll leave it that way. What I'm thinking. Okay, that'll work. It doesn't simplify. I can't go any further than that, but we'll leave it for there. We'll leave it there for now. Let's look at the distance between P and D. It also is going to be found using a distance formula. And from P to D, the line D is going to be the distance between the coordinates xy and the coordinates x negative a. So if I look at the horizontal distance there, the change in the coordinates x minus x, well, there is no horizontal change there. Okay, so that's going to be 0. And y minus negative a, running a little tight to the edge, but I think we can make it. Y minus negative a. Now there's a double negative on that y coordinate there when I subtract it, which makes it a plus. So the x's drop out. This becomes the square root of, well, that's y plus a quantity squared. And if I expand that, that would be y squared plus 2 ay plus a squared. Okay. Now this is an equation, so I can use properties of equality to work with this. First of all, I could square both sides, and that'll get rid of the root, which is very nice. Okay, so I end up with x squared plus y squared minus 2ay plus a squared equals y squared plus 2ay plus a squared. That's just squaring both sides. Really, I could have just erased the roots. Whatever, it works. And then I'm going to try to group some things together here. First thing I notice is that I've got a y squared on both sides of this equation. I could subtract y squared from both sides, and those will drop off. I can do the same with the a squared. Subtract a squared, those drop off. Okay? And then all I have left is x squared, a minus 2ay, and a plus 2ay. Well, if I were to maybe make everything positive, so I'm going to add this 2ay to both sides. That's going to drop it off on the left. but on the right it actually doubles in value, so it becomes 4ay, right? 2 plus 2. And so my final equation is going to be x squared equals 4ay, right? So now whatever the distance a is between the vertex and the focus, I plug that distance in here, and I'll have an equation that represents that parabola, that particular parabola. That's kind of neat. And so that'll give us a nice equation that we can use. Now, we've seen equations like this, and if you'll recall, sort of our basic parabola, the equation of our basic parabola is y equals x squared, or f of x equals x squared. Well, what does that mean? That must mean that for that parabola, in order to get a coefficient of 1 on this y, I'd have to have the a value equaling 1/4, right? So a must equal 1/4 in order to get 4 times a to be 1 and get this equation. And so that tells me that for our basic parabola that we've looked at before, our squaring function, if you recall from our library of functions discussion, that parabola has a focus. If this is a value of 1, then the focus would have been at 1/4 of a unit, okay, in the vertical direction, and the directrix would have then been at a negative 1/4, okay, and that would get us our basic parabola, all right? So now we have a formula that'll work for any parabola that's opening upward. Now remember, my assumptions here must hold in order for this equation to hold. All right, so we have to have an axis of symmetry that's on the y-axis, so those two things coincide. The vertex is at the origin, and what else do we have? Oh, it's opening up, okay, in order for this to work out. We do have some alterations to this that we can work with. If you recall, we've done a lot with transformations of graphs. And so in order to shift this so that the vertex is not at the origin, all you really need to do is subtract from the variables, x minus a number or y minus a number. In fact, if I erase my assumptions here, and I decide to put the vertex at a different point, let's call it h comma k, because we've seen that before, right? If my vertex is at h comma k, then the corresponding equation is going to be a horizontal shift h, so x becomes x minus h, and it's a vertical shift of k. Now in the past, we have added the k, we add the k in, but instead what we're going to do is we would subtract the k from the y value, right? So we'd have x minus h and y minus k to give the horizontal shift and the vertical shift of that parabola. Now there is one more definition I should really talk about, and that is the distance that gives us the spread of this parabola. And so one way to measure the spread, I'm going to erase a little bit of this here. One way to measure the spread of the parabola, or the width of it, is to find the symmetric points that are exactly on either side of the focus, okay? And so to do that, if I were to draw a line segment that is parallel to the directrix, but goes across the opening of the parabola, that line segment is a good way to measure the width, or at least to sketch in how wide or narrow the graph is. This line segment is given a name. It's called the lattice rectum. Don't laugh, I know. But that's the word that it's called, or the name that it is given. The lattice rectum, yes, there it is. It represents the distance of this opening across the focus, or at the same level as the focus. To find that distance, what we would need to do is figure out what the x values are for each of those points, right? So where's that x value, where's that x value, and of course just subtract them, or because there's symmetry here, we could find 1 and double it, okay? Now how would I do that? Well, I know that the focus is a units high. That's a y value of a. So if I were to take my equation here, plug in a y value of a, so that'd be x squared equals 4aa, right? So y becomes a because that's the height. And now I just solve for x. And aa is a squared, so I have x squared equals 4a squared. Now to solve for x, I use the square root property, take the square root of that, and I end up with x equals plus or minus 2a, right? The square root of 4a squared is 2a. And so what we find out is that instead of a question mark here, if I put 2a, the positive version on the right, negative 2a, the negative version on the left, that will give us the coordinates. And so the lattice rectum itself has a length of 4a, right? 2a in either direction, add them up, and you get 4a. All right, so that will give you that distance. But again, from the focus, it is 2a in either direction.